Hello and welcome to another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 1, Lesson 10 on identities and inconsistent equations. You probably don't know what either one of those things is, which makes sense, right? So there are equations that pop up in math that are weird. They behave weirdly, okay? Now, at the end of the day, right, what I want you to remember, and this is very important, is that the solution to an equation is any value of the variable that makes the equation true. If the value of the variable makes an equation true, it's a solution. And if a value of a variable makes it false, it's not a solution. Those are going to be key to understanding what an identity is and what an inconsistent equation is and how to recognize them. Let's start by looking at an identity. All right, here we go. Strangely behaving equation. Exercise number 1. Consider the equation 3 times x plus 5 minus 1 equals 3x plus 14. Letter A asks us to show that each of the values below is a solution to this equation by substitution. All right, well, let's do one of these together and then have you do the other one separately. And by the way, before we even jump in, let's just talk about how weird this is. Every single equation that you've solved so far has had one and only one solution, and yet I'm claiming that if you put any one of these three into this equation, it's going to pan out to be a solution. Now, that's a little bit weird, but there's lots of equations in math that have 2 solutions, 3 solutions, 4, 5, 6, etc. The weird thing about this equation is it doesn't just have these 3 things as solutions. We're going to find out that every value of x is a solution. But first, let's go through x equals 2 to make sure it's a solution and then have you check -3 and 5. Let's do 2 together. Now, of course, the way that you actually go through checking that this is an equation is you're going to put 2 in everywhere x is to see if it makes the equation true. Well, on the left-hand side, right, we have to do that 2 plus 5 first, which is going to be 7. On the right-hand side, we have to do that 3 times 2 first, which is going to be 6. Then, of course, we have 3 times 7, which is 21, minus 1. Here we have 6 plus 14, which is 20. And that gives us 20 equals 20. And that's true. And because it's true, that means that x equals 2 is a solution. Now, what I'd like you to do is test to make sure that these two are also solutions. Pause the video now and go ahead and do that. All right, let's test x equals -3 and then x equals 5. So for x equals -3, right, we're going to have 3 times -3 plus 5 minus 1 is equal to 3 times -3, where's my parentheses, plus 14. Draw a little line down here so we have some room for the next one. Here, just like before, -3 plus 5 is 2. Here, 3 times -3 is -9 plus 14. Here, 3 times 2 is 6 minus 1. Here I have -9 plus 14, which is 5. 6 minus 1 is 5. 5 equals 5. You bet. Let's do the other one right away. Here I'm going to substitute 5 in for x, so I'll get 3 times 5 plus 5 minus 1 equals 3 times 5 plus 14. Over here, 5 plus 5 is 10. Here, 3 times 5 is 15. 3 times 10 is 30, minus 1 equals 29, and 29 equals 29. So, without a doubt, each one of these 3 values of x is a solution to that equation because it makes the equation true. Let's see if we can understand why. Letter B. Solve this equation by first simplifying the left-hand side. What strange result did you get from letter C? All right, so if I had just given you this equation up front and said, hey, solve it, the first thing I would want you to do, let's go to the board, is I would want you to simplify the left-hand side. So I'd get 3x plus 15 minus 1 equals 3x plus 14. Then if I combine the 15 minus 1, right, I'd get 14. And let's stop right there, because this is all we need to understand that this is an identity. You see, by manipulating the left-hand side, what I see is that the left-hand side and the right-hand side are algebraically equivalent, which means no matter what value of x I put in this side of the equation, when I put it in this side of the equation, the two sides are going to be equal, and therefore the equation is going to be true. So every value of x will make this true. What strange result did we get? Well, we got the same expression on both sides. All right? Anytime when you manipulate an equation and you end up with something like 3x plus 14 equals 3x plus 14, or 2x minus 1 equals 2x minus 1, something that looks identical on one side as it does on the other, that is known as an identity. And identities have an infinite number of solutions, meaning that they just keep going on, and in fact, every value of x or y or whatever the variable is a solution to this equation. Any value that you plug in for x will make 3x plus 14 equal to 3x plus 14. Let's summarize this. Right? An identity. An equation that is always true and therefore has an infinite number of solutions. Now what we want to do is be able to figure out that an equation is an identity without having to solve it all the way through. Let's take a look at exercise number 2. Manipulate both sides of these equations to determine if the equation is an identity. State whether the equation has one solution or an infinite number. You don't have to actually solve the equations. All right, so let's play around with letter A together. All right, I'm going to just bring it up here. So the first thing I'm going to do is I'm going to distribute the 4 through that parentheses, and I'm going to get 4x plus 8. Then I'm going to distribute this 2 through the parentheses, and I'm going to get 2x minus 2. The distributive property. Then I'm going to distribute this through the parentheses, and I'll get 6x plus 6. Now there's really nothing that I can do to this right-hand side. But the left-hand side, I could now do a little rearranging, and I'll get 4x plus 2x plus 8 minus 2 is equal to 6x plus 6. 4x plus 2x is 6x. 8 minus 2 is 6. And look at that. 6x plus 6 is equal to 6x plus 6. Any value of x that I put into this equation would make it true. If I take any number, multiply it by 6, and then add 6, I'm going to get the same thing as if I take the same number, multiply by 6, and add 6. So this is an identity. And because it's an identity, it has an infinite number of solutions. We don't need to solve it any further. We don't need to solve it any further because, quite frankly, any value of x that we put in there would be a solution. Let's take a look at another one, and see if it's also an identity. Let's tackle B together. All right, now on this left-hand side, really, all I can do is distribute that subtraction through the parentheses. Remember how I do that? I negate everything. I change the sign of everything within the parentheses so that 2m minus 3 becomes negative 2m plus 3. Now on this side of the equation, I'm going to distribute the 5. That's going to give me 10m plus 5 minus 3m plus 4. On this side, I can say 10m minus 2m is 8m plus 3. On this side, I'd have 10m minus 3m, which would be 7m. 5 plus 4 would be plus 9. Now step back just for a minute. right? Notice at this stage, we're really at the equivalent stage that we were at here. But what we have on this side of the equation is not identical to what we have on this side of the equation. This means now that it is not an identity, right? And in fact, we could solve this equation and we'd eventually get m equals 6. That would be the one and only one solution, right? So this is not an identity. And it has only one solution. Okay? So the idea is, right, you use the distributive property, associative, commutative properties, right, to simplify one or both sides of the equation. All right? We're not doing anything like the additive property of equality, subtraction property of equality, anything like that. We're just getting it kind of down to this level. If at this point what's on one side is identical to what's on the other side, you have an identity that has an infinite number of solutions. Anything will make this true. On the other hand, if you work it down and you get to this point and you don't have two identical things on this side, then it's not an identity. What I'd like you to do now is I'd like you to do the same thing in letter C and letter D. Pause the video, take as much time as you need to simplify these horrible looking equations and see if either one of them is an identity that has an infinite number of solutions. All right, let's go through it. This thing looks intimidating at first, but it's not too bad. Let's begin by distributing the 7. All right, just use the distributive property. So we're going to have 14y plus 21 plus 3y minus 5 is equal to 5y plus, distribute the 2, plus 6y plus 16. Again, we'll do some maybe rearranging. 14y plus 3y plus 21 minus 5 is equal to, well, here we can just combine. We'll get 11y plus 16. Here, 14y and 3y is 17y plus 21 minus 5 is 6 equals 11y plus 16. At this point, we step back and we look at what we have. If what we have is identical on both sides, identity, infinite number of solutions, moving on. But certainly not the case here, right? In fact, we could go on to solve this. I mean, just think about it. We could subtract an 11y from both sides, and we'd have 6y plus 6 equals 16. We could subtract a 6 from both sides. The answer wouldn't be pretty. It would be fractional, but we would get an answer and one answer. So this is not an identity. One solution. All right, let's take a look at letter D. Well, here, the 12c plus 6, there's nothing I'm going to do with that. I'm then going to distribute this subtraction. 2c minus 8 will become negative 2c plus 8. On this side of the equation, we're going to distribute the 4. We're going to get 8c plus 12. Then we're going to distribute the 2. We're going to get plus 2c plus 2. We got to be careful with all of our distribution. Let me just rearrange a little bit here. I love the fact that a 6 became a D. Very strange. They look kind of similar, but not really. 12c minus 2c plus 6 plus 8. Again, rearranging. 8c plus 2c plus 12 plus 2. Here we'll have 12c minus 2c. That's 10c. 6 plus 8 is 14. On this side, we'll have 8c plus 2c. That's 10c. 12 plus 2 is 14. We step back. 10c plus 14 equals 10c plus 14. Every value of c would make that true, every single one of them. So this is an example of an identity, and it's got an infinite number of solutions. And we'll abbreviate solutions SOLNS. All right. So it's pretty easy actually to spot an identity. You just got to work it, distributive property, commutative, associative, right? Simplify both sides. If the two sides then look identical, we have an identity. And at least in this case, if they don't, then we have a non-identity with one solution. But there's this other type of an equation, and that's what we're going to look at next. If we have equations that have an infinite number of solutions, called identities, then there are also equations that have no solutions, that have no values of the variable that could possibly make them true. Those are called inconsistent equations, equations that have no solutions at all. So let's begin by looking at a very, very simple example of that in exercise number 3. Consider the equation x plus 5 equals x plus 9. Letter A, although this may seem silly, says, show that the following values of x are not solutions to this equation. All right, again, it's a little strange, but let's go through the first one together and then have you do the next two on your own. So I want to show that, hey, not any one of these three is a solution. Now, if I want to see if x equals 5 is a solution, what I'm going to do is, as always, I'm going to put the 5 in for x, and I get 5 plus 5 equals 5 plus 9. 5 plus 5 is 10. 5 plus 9 is 14. Obviously, 10 and 14 aren't the same. That's a false equation. So, x equals 5 isn't a solution. Why don't you go ahead and do this for the values x equals 9 and x equals 0. Just take both values, pause the video now, substitute them in, and show that neither one of them are solutions to this equation. All right, now you may have thought to yourself, this seems a little bit silly, Kirk. You know, we're doing a lot that we really don't need to do, but we'll get into it in letter B a little bit. You know, when we have x equals 9, right, that's going to be 9 plus 5 is equal to 9 plus 9. 9 plus 5 is 14. 9 plus 9 is 18. And that's false. Let's do x equals 0. You know, 0 plus 5 is equal to 0 plus 9. 5 is equal to 9. No, that's false. All right. So all these are false, right? And you probably understand why. I mean, take a look at letter B. Explain why there is no possible number that can solve this equation. In other words, that can make the equation true. Well, how would you explain that to somebody? Like, just think about this for a moment. You don't even necessarily have to write anything down. Just try to explain inside your own head why you couldn't have a solution to this equation. Well, it's essentially this simple, and it should have been something that we saw kind of up here, which is that x plus 5 represents 5 more than x, and x plus 9 represents 9 more than x. And the plain fact is, there is no number out there where 5 more than the number is equal to 9 more than the number, right? There just isn't any number like that, right? If I take the number, 5 and I add 5 to it, I get 10. But if I take 5 and I add 9 to it, I get 14, right? They're different numbers. Same thing, if I take 9 and I add 5, I'll get 14. 9 and 9 is 18. They're not the same. 5 more than a number cannot be equal to 9 more than a number. But what would happen if I actually tried to solve this equation? What would happen if I went through the procedure of solving this equation? Let's do it together. Right? This is an equation with variables on both sides, and most of the time when that's the case, the first thing I'll do is I'll get all the variables on one side. But when I do that, I'll subtract an x here, I'll subtract an x here, and I'll get 5 is equal to 9. Now, we've never had that happen before. In all their cases, when we've been solving an equation with variables on both sides, when I get all the variables over on one side by subtracting typically, right, or adding, then I'm left with some variable on one side. I'm left with, 2x plus 1 is equal to 17 or something like this. In this case, when I subtracted an x from both sides, I got the ridiculous statement 5 is equal to 9. Could the resulting equation ever be true? No, because 5 doesn't equal 9. And that's how you will always know that you have an inconsistent equation that has absolutely no solutions. And what I mean by that is that if I work my equation down, just kind of like I always have, and I eventually get some silly thing, like 5 is equal to 9, or -3 is equal to 17, or 2 is equal to -4, something that is just clearly false, then that means that that equation cannot have any solutions, because there's no value of x that will ever make 5 equal to 9. I hope that we can all agree on that. That 5 ain't going to be equal to 9 even on its best day, and no value of x is going to make it. Let's play around with that in the next exercise. All right, exercise number 4. Manipulate each side of the following equations to determine if it has one solution, those are the normal kind, an infinite number of solutions, those are the identities, and no solutions is an inconsistent equation. You do not need to solve. All right? In other words, we're just looking for these red flags, these things where I've got, 10x plus 2 equals 10x plus 2. Oh, that's an identity. Or 5 equals 7. Ooh, no, that's inconsistent, Let's work on letter A together. All right, so just like before, we're going to start as if we were going to be solving this equation. I'm going to distribute the 3 through. That's going to give me 3x plus 24, hopefully plus, minus x plus 6. No distributing the negative there. There's no parentheses there. And then 2x plus 22. All right, let me do a little bit of rearranging. I'll have 3x minus x is 2x. I'll have 24 plus 6 is 30. And here I'll get 2x plus 22. Now, just step back for a second. One thing I know for certain at this step is that it's not an identity. If it's an identity, it would look like 2x plus 30 equals 2x plus 30. Always true. Here I've got 2x plus 30 equals 2x plus 22. Now if I went one additional step, right, and I subtracted a 2x from both sides, I'd get 30 is equal to 22. And that is false. Always false. Always false. And therefore, this is an inconsistent equation with no solutions. 0 solutions. I know the question didn't ask for that, but I really want to hammer it home. Right? There is nothing that's going to make 30 equal to 22. 0 solutions. What I'd like you to do now, there is letter C, B, C, and D, and that's it, just making sure. I'd like you to work through each one of these 4, simplifying both sides as needed until you figure out whether it's just a normal equation with one solution, an inconsistent equation with 0 solutions, or an identity with an infinite number of solutions. Pause the video now and take upwards of 5 or 10 minutes to do this. Well, that was a fast 10 minutes. Are you sure you spent long enough? Well, let's find out. Letter B. Okay, here we go. Let's do some distribution. That's how we begin. 6m plus 2 plus 3m, I didn't get an 3 or an m, plus 15 is equal to 4m plus, again, a little distribution, 3m plus 3. Let's do some combining of like terms. I have 6m plus 3m. That's going to be 9m. Plus 2 plus 15 is plus 17. This side of the equation, I've got 4m and 3m. That's 7m plus 3. Let's step back at this point, right? At this point, it may be obvious or it may not be obvious what you have. Again, one thing is clear to me, I don't have an identity. If I had an identity, I'd have like 9m plus 17 equals 9m plus 17. I don't have that, right? I also don't have something that's inconsistent, because if I subtract a 7m from both sides, right? If I do that, if I take that extra step, right, I would get 2m plus 17 is equal to 3. There's nothing about that that's weird. There's no like, oh, 30 equals 22 or 5 is equal to 7 or anything like that, right? This equation ultimately is going to have one solution. And you could go on and actually find that solution. It would end up being m equals -7, but you shouldn't need to. You should know at this point, well, it's not an identity and it's not inconsistent. So this is just a normal equation with one solution. All right, let's keep working on these last two, see if they're identities or inconsistent. All right, letter C, let's do our distribution. We're going to get 5y minus 5. Oh, now we have to distribute a subtraction. Watch out there. Minus y plus 2. Another distribution here. 2 times 2y is 4y. Come on, pen. Plus 2 times 3 is 6. Funny looking 4 there. Hopefully you can tell that's a 4. All right, doing a little bit of shortcut. 5y minus y is positive 4y. Then I have a -5 and a +2, which is going to leave me with a -3. On this side, I've got 4y and nothing is combining with it. And then I have 6 minus 9, which is -3. All right, step back, reflect on what I have. 4y minus 3 equals 4y minus 3. Any value of y that I put in here, any value at all, would make it work because the two sides are identical. Therefore, this is an identity. And that has an infinite number of solutions. Infinite number of solutions. All right, let's do that last one. Let's do some more distributive property. Man, we're getting good at that. 4n plus 4 plus 2n plus 6 equals 11n, distribute that subtraction, watch out, minus 5n plus 2. Again, combining like terms, 4n and 2n is 6n. Positive 4 and positive 6 is positive 10. Here I'll have 11n minus 5n is 6n plus 2. And again, there may be some of you that can look at it at this point and say, of course, if I have 10 more than 6n and 2 more than 6n, there can't be any value of n that gets that job done. Now, if that's not clear to you, then go that extra step, because that extra step would say, oh, let's subtract a 6n from both sides. When we do that, we get the silly statement that 10 is equal to 2, and that is always false. 100% of the time, 10 is never equal to 2. Therefore, this is an inconsistent equation that has no solutions. It's strange. You know, all throughout this unit, every equation we solved until today had one solution, and only one solution. Now in Algebra 1, you'll see lots of equations, especially ones that have a squared term on them, have two solutions. And sometimes you might even find some in Algebra 1 that have 3 solutions. And as you move on, you can find ones that have all sorts of different numbers of solutions. In this particular lesson, though, we saw more than that. And let's kind of summarize. Right, we saw equations that had an infinite number of solutions. Those were called identities. Every value of x that we plugged in would have made the equation true and therefore been a solution. And we saw their complete opposite, equations known as inconsistent, equations that no matter how hard you try, you will never find a value of x that will make them true. Both of these types of equations have sort of red flags that tell you that the equation is one of them, but only after you've done a considerable amount of simplifying first. All right. I'd like to thank you for joining me for another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.